Welcome to everyone, and thank you for inviting me. I have the same problem as the previous speaker, Laurent Mas. In other words, it's basically impossible to describe the modeling of magnetic fusion plasmas within an hour and a half, right? So not within a week, actually. So I decided to focus on one topic, which is a question of kinetic MHD, which is, in other words, the way you can implement in fluid equations kinetic effects. And the ultimate step being the so-called hybrid codes, which combine fluid simulations and kinetic simulations. And this is also quite complementary to lectures that were given previously by Jim Callan in particular, Eric Zonendrucker, and also Jean-Marcel Rax. So the outline will be as follows. I will start with a brief summary of kinetic versus fluid simulations, advantages, pros and cons. Then I will address the first step between the usual single fluid approach towards kinetic, which is a two-fluid MHD. And we'll see why there is some kinetic effects are actually included in this description, but still very much insufficient to describe some kind of instabilities driven by fast particles, for instance. Then I will show you how you can implement some physical effect like gyroaverage and closure. Then I will move to hybrid codes, and this is going to be the difficult part. And finally, I will show some examples, and actually I will try to address one type of instability in a tokamak, which is the internal kink mode, and this will be in a sense, a test bed to show how these effects can be implemented progressively, and what are the effects that are associated to each of these improvements. Okay, so let's start with the beginning. This actually was shown already in previous talks. On the left, you have the usual kinetic approach. Okay, so basically you solve Fokker-Planck equations coupled to Maxwell equations, and the charge and currents are calculated by computing moments of the distribution functions, right? And of course, the problem there is that you need to compute distribution functions in principle in a 6-dimensional space, so 3 positions for space and 3 positions for the velocity, time dependent, and that's very costly. As you know, and this has been said many times, in fact, we use Gyrokinetic, so we'll say a few words about that, which is still 5-dimensional, right? So very time consuming. Now, on the right, you have the simplest, I think, the simplest example of fluid simulations, which is a single fluid MHD. So V is the V is the velocity, the flow. Rho is mass density, P is pressure, J is current, B is field. Here, I've assumed a constant viscosity. So there you have a choice. Either you choose a collision of viscosity, which is very small in the tokamak, as Jim showed yesterday, I think. Or you choose viscosity, which is given by a background of turbulence. In other words, what you do with these equations is that you simulate large-scale throws, so big instabilities, and you assume that there is some kind of small-scale fluctuations that are going to give you an effective viscosity, which is like the kind of thing you do in fluid in aerodynamics with LES, large eddy scale simulations. And nu in that case is of the order of 1 meter square per second. Now for the field, that's also very classical. Here eta is the resistivity, that's very small, right? So eta over mu naught is the diffusion coefficient for the magnetic field, and it is something between 10 to minus 3 to 10 to minus 2 meters square per second. In a tokamak. So notice that in this talk and what will follows, d over dt will be a Lagrangian derivative that is containing the flow velocity. Now, of course, you need also two extra equations at least. One for the density, which is usually just a conservation of mass, and one for pressure. There you have a choice. Either you decide that pressure times density to the -5/3 is constant. That's normally the usual single fluid ideal MHD you use. Or you use, you implement transport terms, that is heat diffusion coefficient. And of course, the heat, as you saw with Jim Callan yesterday, the heat diffusion coefficients are not the same along the field lines and perpendicular to the field lines. This is what we do in practice. Now, of course, MHD is three-dimensional, time-dependent. This is still quite a big task, but nevertheless easier in principle than kinetic description. So why would you move from fluid to kinetic? The MHD descriptions can fail at least in two cases. One is a case where you encounter, for a reason or another, a Landau resonance. So we have seen many examples in the few days on Monday and Tuesday. So typically when the phase velocity of a wave equals the velocity of particles, right? There is something close to singularity that appears in the phase space and cannot be very well described, or not described at all, by moments of the kinetic equation. Okay. In practice, that means, on the other hand, that if the frequency is very different from the product of the wave number times the velocity, that is, in other words, if you're far from a resonance, then the fluid description is correct, and that will actually occur in many cases. So in fact, if you look to the high frequency limit, which is sometimes called the hydrodynamic limit, so omega, which is a mode frequency much larger than the transit frequency kV, you're safe. I mean, MHD will be correct. Okay. Now, there is another case where MHD may not work, which is a case where the width of the orbits, right, is of the same scales or larger than the scales associated to the mode you're looking at, right? And there is this is quite easy to understand. If I can make a small drawing, if you take the simplest example, just the cyclotron motion of a particle, right, in a field. So this would be a field line, right? And this would be the cyclotron motion. So actually show a better drawing later on. The size of your cyclotron motion is Larmor radius rho c. So this would be this delta actually. And obviously if you have an MHD mode which is small scales, right? Something like that. So this would be the wavelength, which is actually more or less 1 over the wave number. To 2 pi somewhere. Quite obviously, if the Larmor radius, the size of the orbit, is larger than lambda, and also if the motion of your particle is much faster than the time of evolution of your mode, which is usually the case, what is going on is that the particle is going to average the field, right? Which is what is actually called gyroaverage, right? And if you are in a situation where rho is much larger than lambda, that is lambda or much smaller than rho c, the average field that is seen by the particle is just 0, right? Because there is plus and minus everywhere, so close to 0, and that's of course very difficult to implement in the fluid descriptions. Actually, you can do that. We'll see that later on, but it is not included in the conventional single fluid MHD approach, right? So basically, that gives you the second condition, that is the product of the wave number times the scale of your orbit should be smaller than 1, right? Now, why did I choose the notation delta is that, of course, you have other type of trajectories in the tokamak, so-called banana, for instance. In that case, delta should be replaced by the size of the banana, right? And things like that, okay? But that's basically the story. Now, everything to say that at the end, if you look at ideal MHD, which means that you neglect all the dissipative terms here, the viscosity and the resistivity, that means at the end that most of your instabilities will grow with a characteristic time, which is the Alven time, right? So I will give the definition later on. And actually, if actually the growth rate is of the order of the inverse of the Alvan time, you find that actually the first condition is usually fulfilled, at least in a tokamak. Except, and we'll see actually this example, except if you have a population of fast particles like the alpha particles produced by fusion reactions. And in that case, of course, the velocity, which is quite high, right, can match the phase velocity of the mode, right, or the wave. So to summarize this slide, usually the difficulties will occur when you move to small frequencies and or small scales. Okay. Now, you would say for MHD modes, very often these are global modes or large scales, so it should be okay, except that very often there are very small layers, which are called inertial layers, for instance, whose size can be actually below the Lamont radius, okay, in which case you're in trouble. What about the kinetic description? Well, that was mentioned several times. Well, in tokamaks, it turns out that the field is quite high, so the cyclotron frequency is very large compared to the typical frequencies for both MHD modes, or most of them, and turbulent micro instabilities, right? So, in other words, omega C, which is the cyclotron frequency, is much larger than all the omegas. Well, in that case, you can gyroaverage or average, well, this is actually this kind of operation. You can average your kinetic equation and find the so-called gyrokinetic equation, in which basically you forget about the cyclotron phase, although it in fact is still there. You don't lose this information, in fact. But you average over this phase. The adiabatic invariant, or the magnetic moment, is an adiabatic invariant. Okay, and that's very practical. And you're left with 4 dynamical variables, which are typically the gyrocenters variables. So if I draw a field line here, so same kind of drawing as here. Well, this doesn't work very well, right? Anyway. Typically, the trajectory will be something like that. What is called the gyrocenter is the center of the cyclotron motion. First sight, it will follow a field line. So a field line, for those who don't know that, the field line is tangent to the field everywhere, every places. And in practice, this gyrocenter will actually drift away from a drift line because of drift velocities that we'll see in detail later on. Okay. So in practice, what you have to do is to describe, or in a gyrokinetic description, your actual variables will be free coordinates for the position of the gyrocenter, and typically it's parallel velocity. Right? Then for the perpendicular velocity, in fact, you use the adiabatic invariant, the magnetic moment. And the 6th variable would be the cyclotron phase, which has disappeared in the problem. So that's essentially the spirit of gyrokinetic. So I'm not going to detail gyrokinetic because this would be a lecture, and this was actually done by Eric yesterday. Nevertheless, just keep 2 things in mind. That's going to be important, the following. One is that the distribution of particles, the actual particles, is not the same as the distribution of gyrocenters, right? It seems trivial, but they differ actually, in particular via terms which is a polarization term, which is very important. The second thing is that the charge densities, okay, of true particles, actual particles, are not the same as those for gyrocenters, and that's very easy to understand if you take a box here, right, with your particles here, and the blue curves here represent the cyclotron motion. Well, you can have cases where the particle is inside the box and the guiding center outside, or conversely, the guiding center is inside and the particle is outside, right? So when you are counting particles, especially when there is a gradient, of course, when the medium is inhomogeneous, right, the density of the guiding centers is going to be different from the density of actual particles, and same for the currents. And this, of course, you have to be careful with that, because in the Maxwell equations, what counts is the true density of charge and the true current of actual particles, not guiding sensors. So the difference is not a difficult calculations to do, but there is a difference you have to account for. You can actually also find all these details, I think, in the lectures by Virginie Grand-Girard some 4 years ago here at the SEMRAX. Okay. And there is, of course, if you're interested in that, the overview by Brizard and Ham in Review of Modern Physics 2007. Okay. So now, of course, gyrokinetics is attractive because in principle, you are not constrained as much as MHD by ordering parameters. This is not quite true, especially for MHD. The reason is that, well, the frequency has to be smaller than the cyclotron frequency, as I mentioned before. This is true, actually, for most modes, most instabilities. Now, what is less obvious is that the perturbation amplitude has to be proportional to the normalized gyro radius, which is the ratio of the Larmor radius to the size of your plasma, typically. So which would be actually 1 or 2 × 10⁻³ in ether. So it's a small number. Now, this actually may not be fulfilled, and actually is not fulfilled for some MHD modes. And the reason that if you have a big, and we'll see examples, you will see examples of MHD modes where the displacement of the plasma, right, due to this mode is as big as machine size, right? So the perturbation amplitude does not satisfy this ordering, and that's a real difficulty. So I will come back to that. On the other hand, the big advantage of gyrokinetic is that there is no constraint on the product of the wave number times the Larmor radius, or the orbit width, if you prefer. That's the big advantage. So you can treat, in principle, correctly inertial layers or stuff like that, up to some point. The other disadvantage, which is not that dramatic for gyrokinetics, is that it misses magnetosonic waves. So there's no wave you can treat, and that's not surprising. It's a high frequency wave usually. So there is no way you can describe that with gyrokinetic. But for most of the, let's say, dangerous MHD modes we're interested in, it's not a big deal. Okay, so that was for the first part, and I'm moving now to the second part, which is two-fluid MHD, right? Which is kind of minimum steps towards kinetic physics. Well, strictly speaking, you would say that this is not kinetic. In fact, you will see there is some kinetic ingredients in that. And in particular, we'll see that there are two major things that we can play with is the ion stress tensor, which contains the final Larmor radius effect. And you can also play with heat fluxes, in other words, with the closures that Jim Callan addressed very intensively yesterday. So how do you move to two-fluid MHD? So you have to, of course, the key question is the momentum equation, right? Because the momentum equation for particles is going to give you the Ohm's law on the one hand, and the evolution equation for the flow on the other hand. So you have to go back to the momentum equation for each species, okay, which is labeled by an S here. Okay, so this is mass, this is charge, this is the Lorentz force, pressure gradient, and divergence of the stress tensor. Notice that compared to, I think, what Jim showed yesterday, I separate, normally these two terms belong to the same thing, which is the stress tensor. So I extracted from the stress tensor a diagonal part, which I call pressure. And I put here all type of more or less exotic physics that we'll see for some part, which are not corresponding to this simple pressure term. Okay, so in other words, this stress tensor here is not diagonal and is not isotropic usually. So if you look now at the case which actually would correspond in spirit to gyrokinetic, that is, you move to strong guide field, strong B, which means very large cyclotron frequency compared to all other typical frequencies in the problem. Then you move to the so-called drift ordering. You can reverse this equation. So you assume this is small, this is small, this is small, this is small. So the big thing here is this cross product between the flow and the field. So you can reverse it very easily. And you will find the flow, that is a perpendicular flow plus a parallel flow. So the parallel flow is here, okay? So it's different for each species. And then you have here the very celebrated E cross B flow, which is just E cross B over B squared, right? Then you have something we have already met twice. I think it was presented in a lecture by Jean-Marcel Rax, and then in the one by Jim Callen, which is a diamagnetic velocity, which is given here. So it's a cross product between the field. This is a unit vector along the field. This is pressure gradient, density, charge, field. Right? Plus plenty of other terms, which supposedly are small. And I didn't put here one, which is coming from the time derivative here, which is the inertial term that you have to keep in principle. Now, the question is, how do you define now the MHD flow? And actually, there are several choices. One that is intuitive is to say, well, the E cross B flow, as you can see, does not depend on the charge number, right? Nor, let's say, on the density. So it's the same for all spaces. Okay. Whereas you see for the diamagnetic frequency, it does depend on the charge number. For instance, in particular, electrons are not moving in the same direction as the ions, right? So it is tempted to say that to choose an MHD flow, at least for the perpendicular part of it, equals to the E cross B flow. So that's what I'm going to do in the following. But there are other choices, as I will say. And for the parallel velocity, there you have choices, but it makes sense to choose the ion velocity because ions carry mass, the mass, right? So in terms of the flow, it makes sense to choose for the parallel velocity of the MHD flow, the ion velocity. But it is a matter of definition, right? It's a matter of choice. And there are several choices which are possible. In particular, in some textbooks you will see, or papers, you will see that the MHD flow is actually the ion flow. So it does contain the ion diamagnetic velocity. Okay? So let's start with an assumption, or let's say a definition, I should say, of the MHD flow, which is just V, which is V equals B plus the ion parallel velocity times B, B being, small b being the unit vector along the field. And in that definition, then the ion flow is the sum of the MHD flow plus the ion diamagnetic velocity, plus plenty of corrections. Okay? And the electron flow, well, that's the easy part. Because in principle, what you like to manipulate or to play with in MHD is a current. Because the current is related to the magnetic field, right? Via the Maxwell equation. So the simplest thing is to use the definition of the current, okay, and say that the electron velocity is related to the ion velocity and the current, right? Divided by, of course, time, divided by the electron density times the charge. Here the charge is a positive charge, right? It's 1.6 10 to minus 19 Coulomb. So if you now use these definitions and you start from the electron momentum equation, this one here, you forget at the moment the stress tensor, which for MHD is not too bad in tokamak, but for instance in space plasmas they do keep that. The gyroviscous tensors for electrons. You get a generalized Ohm's law, which is very well known and you can find in textbooks. So it starts as before, that is eta J. Eta is, I remind you, the resistivity, equals the electric field, the Lorentz force, V cross B. And then there is a new term here, which is the so-called whole MHD term, and actually plays an important role for reconnection, and we'll see actually an example. Electron pressure gradient, and a term here which is the electron inertia. I'm not going to insist very much on that, but we'll see that it may play some role in some cases. G squared here is the electron skin depth, so it was also introduced in Jean-Marcel Rach's lecture. It's C squared over omega P squared, where omega P is the plasma frequency, right? And it's quite small. This is still a bit complicated to implement in codes. Some do that, but it's still a bit technical. You can move to simplified expression using the drift, which is called drift MHD, by using this kind of expansion here. And if you do that, that is, if you extract the ion velocity, right, using this expression here, and the expression of the diamagnetic velocity, which was given before, you arrive to something which is much simpler and actually very close to the usual resistive MHD. So basically, this is what we used implicitly in single MHD, so E plus V cross B. And here you will find a correction which contains the so-called electron diamagnetic effects. So this is not easy to see like that, but so probably I should, is there some eraser somewhere? Well, here it is. The reason is that if you consider a very simple example, so constant magnetic field, right? And you look essentially at magnetic perturbations which are perpendicular to the guide field. So in that case, delta B vector is going to be the curl, well, in the US notation would be something like that, times the vector potential times the unit vector B, right? So if B is uniform, then it's very simple. You find grade A parallel, vectorial B. Now, if you look at the corresponding terms here, delta B, so for the perturbed part, so delta B over B, grad P over NE is something like 1 over NEB. Then you have something like that times grad PE. But this, of course, you can rewrite it as 1 over NEB, B vectorial grad PE over B. Well, the B is already there, so I don't need to do that. And grad A parallel, right? Now this here is the diamagnetic velocity for electrons up to 2 sign, right? So it's linear star electrons. And if you look now for E, the electric field starts with something like minus dA parallel over dt times B minus grad phi potential. So if you look at this, so there is a time derivative of your vector potential, and then here you have an advection of your vector potential at a speed which is the electron dynamic velocity. Now if you do the same exercise for this term here, the V cross B, this one here, okay, you recover in some kind an extension of the frozen-in law for MHD, except that what it says is that the vector potential is going to be advected at a velocity which is essentially the electron velocity, right? So the sum of the MHD flow plus electron dynamic velocity. That's why usually it is called, or it is said that it produces electron dynamic effects, right? And the main thing is that if you look at a mode who is very strongly dependent on this Ohm's law, its frequency or phase velocity will match the electron velocity. So that's for the Ohm's law. It gives you one part. And then you have to move to the ions. And that's a bit more difficult to say so. So I've tried to summarize the situation. So the situation is that the momentum equation for ions starts like this. So this is ion pressure gradient, this is Lorentz force. And there you cannot neglect the stress tensor, no, which is kind of complex. But even if you ignore collisions, right, there is one part which is going to depend on the very sensitively on the Larmor radius time, the wave number, which is a gyroviscous stress tensor. And I think it was given in your talk for part. No, it was not given. Okay, so it will be tomorrow. Sorry for that. The schedule is not perfect. Anyway, so this is kind of an intricate expression. So I didn't give it back in the slides. You can find it in the paper by Zeltins and in the book also by Zeltin Mies and as a textbooks on this question. Now, there, of course, you are in trouble. Turns out, it was realized that at least in the case where of a slab geometry where the magnetic field is not curved or uniform, there is an exact relationship which relates the divergence of this stress tensor, so gyroviscous stress tensor, to the diamagnetic flow, diamagnetic and MHD flow. So V is the MHD flow, V star is the ion diamagnetic flow, rho is the mass density, sorry. It's a bit complicated, but tractable, right? And you will see that also, as you can see here, there is also a small term here, but that you can, which is quite small actually, and that you can incorporate in the pressure. Right? So if you combine this equation here, and you can find the details in the paper by Zeltin in '85, and as a papers on the same subject. You will recover something which is usually found in the literature for MHD. So for the mass density, well, it's just mass conservation, where the flow now is the ion flow. So that's the mass density conservation for ions. And V is the sum of the MHD flow plus V star being the ion dynamic velocity. And the big change here is on the momentum equation here. So it's the same as before, but there is another extra term, which is this one here. Now, this will contain the so-called ion dynamic effects, right? And the reason for that is actually easier to understand that for electrons is that, as you can see, right, in terms of advection, you have an extra term, which is a V star grad. So same thing. If your physics is, of the mode is essentially tied to the ion physics, what you will find that the phase velocity of your MHD mode will be tied to the MHD flow plus the ion dynamic velocity. Right? Now, if both effects, electron dynamic effects and ion dynamic effects, are important, then it's going to be a compromise in between those two. Right? And actually, it will depend on the type of modes you are dealing with. Now, the reason why I was saying at the beginning that doing that, you incorporate a bit of the kinetic physics is that, in a sense, what you're doing in this operation by using the gyroviscous stress tensor is that you are accounting for finite Larmor radius effect, which is part of, well, I've raised it, but part of the physics that is associated to this gyroaverage process in which the particle average the field over its cyclotron motion. Okay. Now, these effects, ion and electron dynamic effects, are very, very important in the sense that even linearly, they actually change the stability, and they are usually stabilizing. The growth rate is smaller with dynamic effect than what you would find, for instance, in single free MHD. Now, the problem is that, unfortunately, this is true in slab geometry uniform field. That's the case where you can demonstrate things clearly and neatly. But in practice, of course, the curve, especially in tokamak, is not at all uniform, right? There is curvature. So usually what people do, that they keep this type of equation and they use it in the curved field, right? In the tokamak. And of course, this raises a problem, right? Because that means that in practice, you're making a small mistake, more or less small, on your growth rate and on the nonlinear dynamics. Now, of course, you can develop equations with curvature, right? But these are very intricate. Right? So you can find them, well, there are several papers there, but at least you can find them in the paper by Ramos in 2005. And if you give a look at it, you will see that if you want to implement that in the code, I mean, it's going to be a long, long way. So in practice, what people are doing is that they use this equation here, plus also pressure equations for electron ions, which also contain corrections due to dynamic effect. These are quite easily to derive from if you use in particular the entropy as a variable, exactly in the same way as Jim did yesterday. You recover these corrections very easily. And for the Ohm's law, very often you will find that it is this equation that is being used. Then of course, you use rho E equals minus dB over dt, right? And you recover the usual equations for in the MHD spirit. How much time do I have now, Bruno? 1 hour. Okay, that's good. Very good. Now, this is not in principle sufficient, right? We still have two problems pending. One is the case where the wave number times the orbit width is of the order of 1, right? Because the gyroviscous story cancellation, as it is called, is going to be okay for k rho I smaller than 1, right? Finite, but smaller than 1. So there, of course, people have been thinking about that. It's not an easy problem. And basically, this is called as Gyrofluid modeling. The idea is to use, instead of using the actual fields, is to use the so-called gyroaverage fields. And there, of course, there is a problem. The problem is that, well, I should really have kept the initial drawing. The problem is that if you look at the cyclotron motion, right, so the one I should have kept, so this is your field line. That's the cyclotron motion. And as I said, the size of the cyclotron motion is mv perp over EB, right? But v perp here is a perpendicular velocity of a particle, not the fluid velocity, right? Obviously. So in principle, if you want to average, and I think Eric mentioned that, but he didn't give, I think, the detail, is that so you separate the position of the particles, right, in guiding center plus cyclotron motion. And the cyclotron motion would be, in the simplest case, would just be, you know, the Larmor radius times E1 times a cosine omega ct plus another vector sine of omega ct, where E1 and E2 are two vectors locally perpendicular to the field. Right? Now, if you take a field, let's say an electric field or electric potential, let's take a scalar, it's simpler. So if you take a field for the gyroaverage of phi in the simplest definition that you can imagine, which is going to be a function of xj and mu, because, or v perp if you prefer, times t, and hopefully I'm not forgetting something, is the average of a cyclotron phase, right, of phi, the actual electric potential of xj plus cyclotron motion in time, right? Now, if you move to the Fourier space, right, so you Fourier transform your field, and you use the simplest expression for the cyclotron motion you can use, it's very easy to check that essentially phi bar in the Fourier space, so k being the wave number, right, depends on time as well, and on mu, so it could be k mu times, is a Bessel function of zero order, k perp rho I, or rho c, sorry, times the Fourier transform of your initial field times t, right? This is just because the Fourier transform, you know, of or dphi or derive an exponential of a cosine or sine is going to give you this Bessel function, right? And the argument of the Bessel function is k perp, which is the perpendicular, wave number, times the Larmor radius. At this stage, here is the trouble. You see the rho c depends on the perpendicular velocity of the particle, not the flow. So the trick is, or it turns out that if you look at gyrokinetic in many cases, not many cases, in some cases, sorry, what counts is something like the square of this J naught, so average over the velocity times the Maxwellian. So it's an average over the phase space of the square of the gyroaverage operator. That's what counts in many cases. Now, it turns out that this is an analytical result. The calculations gives you an explicit expression for this operator, which is just this gamma naught here. This gamma naught here, which is exponential of minus the argument times modified Bessel function. And the argument here is k perp squared times the thermal value of the Larmor radius, here for the ions, squared divided by 2. The square root here comes from the fact that, you see, it's an average of J naught squared, and you're interested in a J naught or an effective J naught, so you just take a square root of that, right? So that's why it's gamma naught 1/2, which counts, okay? So in a sense, at the end, a kind of proxy for the gyroaverage operator is going to be something like that, where you, in the Fourier space, you multiply by your field, by this thing here, and you get this phi bar, and then you go back to the real space, right? Now, if you want to write the equations in the proper way, then you follow more or less the procedure that Jim gave yesterday, except that usually people do that without the collision operator. I understand this is one of your concerns. So they do that in the collisionless regime. And what they get, okay, is a set of equations, which are gyroaverage equations, which are going to replace the equations I showed before. Now, what is the advantage of that? The advantage of that is that if you look at the Fourier, the Taylor development of this function for small k rho I, which is a MHD limit. Remember, MHD limit is k times orbit width smaller than 1. So let's take the first term of that. Right? So this would be here, the 1 minus b over 2, which is here. Right? And incidentally, I didn't mention my source, but this is coming from a paper by Darland in '93. Okay. If you look at the actual expression here, square root of gamma naught, this is the line here, right? The solid line. So as long as your argument is small compared to 1, you're safe, and that's normal. You recover conventional MHD in that case, or conventional fluid, I should say. But of course, when you move to large arguments, that is large values of k rho I, right, you can see that the actual value is 0, and that corresponds exactly to what I told you at the very beginning. That is, if you gyroaverage a field with very small scales of the cyclotron motion of particles, basically the effective field is 0, right? So you recover, of course, quite simply this expression. Now, if you're not happy with this business here, which is in the Fourier space, in particular because you're working in the real space, for instance, what you can do is some kind of so-called Paddy representation, which was actually proposed by Darland as well, which you see consists in replacing this function here, but just something which is 1 over 1 plus b, or 1 over 1 plus b over 2, which in real space is just this argument here. So in that case, what you have to do is just to invert a Poisson equation to recover your field here, phi bar, as a function of the initial field, right? And this is very tractable. Actually, this is actually used in Gyrokinetic as well in some cases, except that you replaced, well, this should be, it should be rho I squared. It's the same as this one here. And in Gyrokinetic, you would put a rho C, which depends on the perpendicular velocity. Right? Now, there's been a long history around these equations. At the end, they're not really used in the tokamak community for MHD. They are used in the space plasma context. In particular, the latest version I am aware of is the one by Passot and co-workers, who are not far from here, actually. They are in Nice, which are, and who are using that for modeling solar winds. So now I'm moving to the second part, which is how can you implement at least a bit of some physics of the Landau damping in fluid equations? So you are going to tell me this is impossible, right? It's not quite true. You can try to do something like that, although it's not fully satisfactory, which consists in changing the closures in your fluid equations compared to what Jim showed you yesterday, right? In particular, the heat flux. So the idea is in fact quite simple. So you can do that as an exercise if you want. You start with 1D Vlasov equation, for instance, right? The 1D Vlasov equation is here. This is V is the particle velocity, and this is the electric potential, right? So very simple thing. And you know the linear solution of that, right? Which is the plasma dispersion relation, which was actually showed by Eric Zenendrucker yesterday as well. Now you can do another exercise, which is to take the n moments of these equations, so, right, which are those moments here, and then you're back to the same problem. Of course, there is a question of closure, that is each moment evolution equation for one given moment depends on the moment of order n plus 1. So if you just take the 3 first moments, so density, velocity, pressure, you have to say something on the moment n plus 1, which is related to the heat flux. So you have to say something on the heat flux. Now, same thing, if you can, of course, exactly solve the linear response of the system for these fluid equations, right? And then it turns out that for the plasma dispersion relations, you know an expansion, or expansion is probably not the right wording, is a continuous fraction representation of this function, or Padé representation, if you prefer. And then what you can do is to compare the two expressions, the fluid one and the Padé representation, adjust the coefficient in your closures, right, to recover the Padé expansion of your distribution of the plasma dispersion relation. The big thing that in principle a continuous fraction expansion is correct for both a Taylor development at small arguments and also for the asymptotic expansion at large arguments. That's the big point. So in principle, you get correctly the two asymptotic limits. Now the problem is that in fact you have several choices possible in the problem, and in fact people have produced closures and for each type of problems they were looking at, or each type of considerations, they were producing different type of closures, right? So in that, if you look at one of the first paper on that by Hammett and Perkins in 90, it was exactly what I said. It was a comparison between the linear response kinetic and the linear response fluid. But you can also have other choices. One by Ron Volz and co-workers was to actually match the instability growth rates, because in his mind that's what counts for a turbulence problem. So you find something close, but not the same as Hammett-Perkins. You can also match your closure in order to find the right flow damping, in particular the so-called zonal flows in tokamak. That was the spirit of the work by Sugala. But you can also try to match the entropy production rate. It turns out that in that case, you actually recover exactly the same as Hammett-Perkins. And that's actually an example where you compare the kinetic entropy production in red and the fluid here results here as a function of the frequency omega for the linearized problem, right? And you find it's not too bad, it's not perfect as well. Right? Now, the most famous one you will find in the literature is the one by Hammett and Perkins, which is something like that. So divergence of flux is going like the minus of a very strange operator here, which is noted in the literature as absolute value of gradient. This is kind of a weird thing. It's easy to understand in the Fourier space. That in Fourier space means absolute value of the wave number. Then you can reconstruct it in the real space, and it's not non-local in the real space. Right? But anyway, that's essentially the one that has been used in the literature, both in turbulence and MHD by Bondeson, for instance. And here you find, actually in the same paper by Hammett and Perkins, this is either directly the plasma dispersion function or something close to it, function of this parameter omega over kV. Here, these lines here would be the exact plasma dispersion function or Friedekon function. The actual disclosure here would be this line here, the dashed line here. Now, if you go to the next moment, that is instead of stopping at the third moment, you move to the fourth order. Then you get something even better, which is this line here and the small dashed curve here, right? So that's actually the most advanced work in that spirit that I know about is the one by Passot again in 2004, 2005. But as you will see, it's extremely intricate. I mean, very intricate. Now, I should say that in practice, as far as I know, today, it's little used for MHD simulations. I think only very few codes which try to implement this kind of thing. There are some reasons for that. I don't know all the reasons for that. But at least in the turbulent context, what was shown at the time is that this works well in the linear situation, and it's not surprising because it was actually built to match the linear response. But in the non-linear regime, you can find quite huge discrepancies between the kinetic result and the fluid result. Right? So it's not completely satisfactory, but that's the best I know about. Right? So at the end, in summary, two fluid equations, two fluid MHD is going to give you at least the necessary correction, which are the diametric corrections that you really need for finding something physical in your growth rate. In principle, you can implement some of the physics associated to gyroaverage and Landau damping by changing the closures and also replacing your field by gyroaverage field. But this is not done that much in practice, right? Now I'm moving to, in a sense, the most difficult part, which is a case where you really have a resonant interaction between an MHD mode and a population of particles. Let's say, for instance, energetic particles typically in tokamak. Right? And there you have to move to hybrid codes. So what is an hybrid code? An hybrid code is maybe is a combination between, or coupling between the fluid code, MHD code, and a kinetic code that's going to represent a given population. So typically, just to fix the idea, you may decide that the thermal electron and ions in the tokamak are going to be modeled with a conventional MHD, B-fluid MHD, and fast particles, for instance, the alpha particles produced by fusion reactions, are going to be a model with a kinetic code. Very often, in that case, on that kind of situation, the kinetic code will be a peak code, a Monte Carlo code, a particle inside. Now, how do you couple them? Well, it's not that complicated. In practice, at least at the lowest order you can imagine, when you look at the problem, you add, again, a stress tensor here in your momentum equation. Here at the moment, I've removed everything that has to do with viscosity and the two-fluid effect. Of course, when you really have to solve the problem, you have to add the ion dimagnetic effect and the viscosity. But I just wanted to focus on this term here, which is just the stress tensor of associated to the fast particles. And a quite good proxy for this stress tensor is a CGL approximation for Shu-Goldman-Low stress tensor, which is given by this expression here. So it's diagonal, but with different coefficients along the field lines and perpendicular to the field lines. So P parallel is the parallel pressure, and P perp is the perpendicular pressure. Now, P parallel is just a moment of the distribution function for fast particles. So V parallel is the parallel velocity along the magnetic field. And P perp is, well, the same thing in the perpendicular direction, right? So if you have computed on the one hand the distribution function for fast particles, right? You can obviously compute these two quantities, okay? Compute the divergence of your stress tensor and put that in your fluid code. Now, I should say you can also, in that way, with this stress tensor, you can implement other effects, in particular the so-called neoclassical effects, which are actually a way to compute the collisional transport in tokamaks, accounting for curvature and trajectory effects. And I think we'll talk about that more or less tomorrow. So doing that, you have one way, that is, you know how to couple your kinetic code to the MHD code via the divergence of the stress tensor, right? Probably, how do you now provide information from the MHD code to the kinetic code, right? Because in principle, an MHD code calculates as we saw, the magnetic field, and from the magnetic field and the velocity, you can calculate the electric field. The problem is that the kinetic code, at least gyrokinetic code, do not work in that way. And actually, we saw that yesterday in the talk by Erik Sonnendrücker. If you look at the equations for the motion equation for the guiding center, or gyro sensors, I should say, you find something like that. So this is the position of the guiding center, and that's its parallel velocity. Now, there is something which is actually along a field which is not exactly the equilibrium field, right? And this actually contains a curvature drift. And there is a perp part here, perpendicular part, where lambda is an effective Hamiltonian. And in this Hamiltonian, you find the magnetic moment, so in times the magnetic field, equilibrium. This is actually going to give you the grad B drift. And here, this is electric potential. This is going to give you the E cross B, or part of the E cross B velocity. And this actually is the parallel vector potential, and that's going to be associated to the physics of field line bending and the fact that the particle along the field lines are following the guiding sensors, are following the field lines at first sight, right? And if you change the direction of the field lines, of course, this will produce a perp motion compared to the equilibrium field. And here is a compressional part associated to the parallel modification of the parallel magnetic field, and actually the same family of as this one here, right? Same thing. Now, the thing is not so much to look at these equations in detail, been discussed many, many times. The thing is that you see the key quantity here is the electric potential and vector potential. And that's not surprising because it's an Hamiltonian theory, okay? And as Jean-Marcel mentioned on Monday, I mean, as long as you want to look in the resonance, the right formalism is Hamiltonian approach, the Hamilton approach. And there, of course, the Hamiltonian perturbed Hamiltonian is just electric potential minus velocity times the vector potential, phi minus VA, right? So it's not surprising that it appears under this form. The problem is that it's not at all what is calculated by an MHD code, right? Of course, they are related. If you know the vector potential and the electric potential, you can calculate the electric field and the magnetic field, right? Obviously. But if you know E and B, you can reconstruct, of course, this potential, but that's kind of tricky, right? So that's one problem. That is, this is not really the appropriate formulation in principle. And the second difficulty is the question of ordering. In the gyrokinetic ordering, normally all these ratios, so mode frequency divided by the cyclotron frequency, parallel wave number divided by perp wave number, but also all perturbations, I didn't put the one on vector potential, but all relative perturbations go like rho star, which is 10 to minus 3. And as I mentioned at the beginning of the talk, this is not consistent with the MHD ordering, because in the MHD ordering, well, K per pro S is in principle smaller than 1, gyrokinetic is order of 1, well, that's fine. It's not forcingly inconsistent. The problem is that if you combine this ordering here, K per pro S of the order of 1 in gyrokinetic, that is small scale perturbations, and the small perturbation here, constraint, you find that the flow, the perpendicular flow, normalized to the thermal velocity, or the sound speed, if you prefer, up to numbers, is small. It's of the order of rho star, 10 to minus 3. In other words, in gyrokinetic, all the flows are slow, or should be slow. Now, in the MHD ordering, that's not at all the case. The usual ordering you find in textbook is that the flow divided by the sound speed can be up to 1, and it can be even larger. I mean, if you look at the reconnection problem, it can be even Alvenic, right? So, well, in practice, if you look at the tokamak, most of the flow are more in this ordering, including the effective Alven velocity for reasons I have no time to explain. But anyway, there is a real difficulty here, which in principle should be dealt with, but very often is not. So how do you solve that? Well, one thing is that you can replace your MHD equations by so-called reduced MHD. So reduced MHD is just that instead of solving on vectors, so the flow, velocity, and the magnetic field, you solve on scalars, which are essentially going to be electric potential, vector potential, density, pressure, parallel velocity for the ions. Could be more as well. But essentially, what the important message here is that in reduced MHD, you get directly the electric potential and the vector potential, and then parallel vector potential. And then you can implement that directly in the gyrokinetic formulation, the usual one, right? So that's one way. And there is a whole category of kinetic code, or hybrid code, which uses this approach. The other one is to use another formulation of the gyrokinetic equation. I'm not going to enter too much in the details, but in these formulations, you actually solve your equations using the actual electric field and the B field, gyroaverage. Okay. Nevertheless, the problem of ordering I was mentioning before is still in the air. There are attempts, as far as I know, to write gyrokinetic equations in a different ordering, that is, in ordering where the flows can be sonic. Right? Well, this is kind of, at least those I've seen, the papers I've seen, are kind of a nightmare, frankly speaking. So it's not done in practice. So on reduced MHD, I'm not going to insist too much, but essentially this is the simplest example you could imagine. I mean, you write your flow as this is case of uniform field. So Z is the direction of your field, equilibrium field. And you find that V is essentially the Ez cross grad phi. Phi is the electric potential. So phi plays the role of the stream function in two-dimensional incompressible hydrodynamic. And you do the same thing for the field, where psi would be related to the vector potential up to a normalizing factor. So in this very simple case, as you can see, you find these two equations, which are just equations of a psi and phi, right? And then you implement that in the, once you have at each time step, you have your psi, your phi, and you implement that in the gyrokinetic code for the dynamics of fast particles. So that's one way. The other way I'm not going to insist too much, but it's just to look at the structure of the equations. This is another formulation for the gyrokinetic equation, which was proposed by Ham in '88. And as you can see now, the big difference is that you are directly handling an E field, electric field here, which is a gyroaverage electric field, but it is something that you can compute quite easily, knowing the E field calculated in the MHD code. And the other thing is that if you look at the Hamiltonian here and B star, you find that all this actually depends on the actual field. So B equilibrium plus this is actually the B field that you calculate in the MHD code, right? So and if you look at the literature, so in a sense there are two schools. One is using reduced MHD, and the other school, in Princeton for instance, or in other places as well, they use this set of equations for the kinetic part, right? And that way you solve the problem. But still, the ordering is the same as the conventional gyrokinetic. Okay, so I think I finished with the question of deriving equations. It's a bit cumbersome. I apologize for that. But the summary of that there are several steps. The simplest step is two-fluid MHD. That's well known. And with this, you will get kind of minimal ingredient to find the correct growth rates, at least in linear regime, but also non-linearly you will find, as we'll see, you will find relatively good descriptions of what is going on in MHD. Now, if you encounter a problem where there is a true resonance between particle and waves, which is the case with energetic particles in the tokamak, then you have to move to an hybrid code, right? And this, of course, is much more complicated. There is a step in between, which is the story of using Landau fluid modeling, which in practice today has been very fashionable at some time, but in practice today is not used that much. So now I'm going to try to illustrate that with one type of instability, not the most dangerous one actually in the tokamak, which is the internal kink mode. So just a few reminders, maybe they are not reminders actually, for the tokamak geometry. So it's a torus. And essentially the equilibrium is such that the Lorentz force balances the pressure gradient. Now the field lines are twisted on magnetic surfaces, and the twisting number is called safety factor. So it measures the number of turns in one direction, toroidal direction, to the divided by the number of turns in the poloidal direction, right? And each magnetic surface, so they are nested around a so-called magnetic axis. Each magnetic surface is at equilibrium, so without perturbations, isothermal, isopressure, okay, isodensity, and so on. So typically it corresponds to this kind of picture. So very often I'm going to show poloidal cuts. So we call toroidal direction the one around the symmetry axis of the torus, and poloidal direction is a cut, a meridional cut of the tokamak. So that, and very often I'm going to show maps, right, on the poloidal plane. So what is the kink mode? I'm not going to enter the details, but the kink mode is essentially driven by the current in the tokamak, and it corresponds to a displacement of your plasma, an helical displacement in the plasma, and this helical displacement and has an helicity, 1, which would correspond in terms of field lines to a safety factor equals to 1. In other words, a field line that would actually make one turn in the toroidal direction and one turn in the poroidal direction to beat its tail, to bite its tail, sorry. So this would actually correspond to one surface, which is one here in the dashed line, right? So the starting point here is a very simple thing. So a set of magnetic surfaces nested with circular geometry in that case. Okay, and because of the instability, the core region here, which is the hottest part, that's where you, in principle, you get your 20 or 10 to 20 kV, is actually displaced. So here in the right, so remember it's helical in practice, right? So it's just a cut in the poloidal plane. So at the same time, it is actually moving in this direction. There is a reorganization of the magnetic topology, which is called reconnection. So reconnection in practice is a change of the connectivity of your field lines. So what is going on in practice is that this part here, which corresponds to the hottest part, is reorganizing with other magnetic surfaces coming from outside. Actually, it is this part that is moving, in fact, and the building up this part here, which is going to replace progressively the hot core. So when you do that, so that's what is going on here. So you see the part here is shrinking, and at the end you are recovering the initial situation, except that, of course, the hottest part here, the highest. Well, I think it's out. Anyway, the part close to the magnetic axis, which is the hottest part, okay, is expelled. So when you're back to this state here, the temperature is completely flattened, right, and the density as well in the core, right. So this actually is not easy to model. We'll see an example. Now, the second thing, and that's why I choose that as a test bed, is that if you put fast particles, alpha particles, for instance, in your plasma, you can excite this type of modes, which then I call fishbones. So this is actually coming from experiment. I have still 20 minutes, right? Oh, yeah, good. So it's a measurement of the density using radar techniques or reflectometry. And here what you have here is essentially, so it's working again, good. It's essentially a cut of the, or three-dimensional plot of the density profile, okay? So you see during this phase here, so this is time, so that's the temperature, that's the density. So you're typically building up your density. As you can see, the motion here is kind of unbalanced, right? This is actually correspond to the beginning of the instability. This is more pronounced here. You see, it's larger and larger, and then suddenly up, you see a crash. That is, the whole thing is erased, right, or flattened. So basically, this reconnection thing, that is this reorganization of the magnetic topology, is actually taking place over a very short time scale, typically 100 microseconds or something like that. And then there is a recovery time, which is much longer, right? It can be 100 milliseconds or something like that. So typically, what this is essentially a relaxation oscillation, right? Best example being, for instance, the Van der Pol oscillator. So the thing is, you see, what is difficult here is to reproduce, well, not only the dynamics of the recovery phase, which is not the most difficult part, but the difficult part is to model this crash phase, and as you could see, this crash is very complex, right? Now, if you look at the temperature, you see this kind of, this is the central temperature versus time, right? And you see that for each crash, right, you're losing, of course, you're decreasing your temperature in very fast time scale. And at the end, that's why we, of course, are interested in that, is that it's detrimental to confinement. That's not good to decrease the temperature precisely in the region where you want to produce fusion, right? And also, but you can deal with that. Actually, ITER is designed to reach its objectives with these crashes, or events, which are called SOTIS. But the second thing is that they may produce secondary modes, which are neoclassical altering modes that Jim Callan mentioned, I think, in one of his talks, which could actually be dangerous, right? Could lead to disruption, that is a termination of the plasma, but also can degrade the confinement. So that's why we are interested in that. So in short, this phenomenon has a long history, and actually, by the way, it is related also to the solar flares in solar physics, right? Same process, reorganization of the magnetic field and expulsion of a good deal of energy, right? Now, obviously, in solar flares, it's much more violent than in tokamak. That's the good. These are the good news. But the thing is that there's been a theory for a long time, one by Sweet Parker, and the tokamak version was proposed by Kadamsev in '70, which tells you that the reconnection time, which I'm going to call crash time, well, you have to be careful. There are two phenomena there. One is the reorganization of the field, and one is the expulsion of the heat, of the pressure. But anyway, let's call this crash time. So the ratio of the crash time to a resistive time scale goes like 1 over square root of the Lundquist number. So just to give order of magnitude, the resistive time scale is just the time you will need to reorganize your field over a length which is the length of the Q equals 1 surface divided by the magnetic diffusion coefficient. This is 100 seconds, something like that, in ITER, or in jet, sorry. And the Alvan time is a ratio of the major radius of your tokamak divided by the speed, the Alvan speed. And this is around 10 minus 6 seconds. I think it's close to the number that Jim gave you some time ago. The Lundquist number is a ratio, it's a dimensionless number, it's a ratio of those two times, right? It's huge, 10 to the 8. And then you see immediately the problem, right? Is that if you look at this ratio here, you are trying to simulate a situation where there are two very disparate timescales, right? And you want to simulate that in the best way possible, right? And I didn't put it, but the width of the inertial layer, the region where reconnection is actually taking place, is 1 over square root of S as well, which means that it is a very, very small region where actually all the inertia effect we are talking about are important, right? Now, in practice, if you compare the theoretical prediction by Kadamsev to the actual reconnection time measured, right, there is a huge difference, right? So the observation is 100 microseconds, and Kadamsev would be something like I think it's a resistive time minus 10 times 10 to minus 4, so it's 10 to minus 2 seconds, right? So there is a huge difference. The question is why? Well, the why is actually related to at least the two fluid effects I was mentioning before. That's why we are interested in that. And this is actually well known now. It's been probably in our context found by Eidemir in '92. But then recovered by many people. And actually, if you look in some recent simulations, you find that indeed, if you look at the width of the island, which is a structure that is growing progressively and replacing the hot core as a function of time, if you look at the pure resistive case, which is a red line here, right, you find something which is almost algebraic, as it should actually. And in the case of B fluid, at the beginning, you find something which is lower, and that's because diamagnetic effects are stabilizing. And then at some point, you find a huge speed up of the process, right? So at the end, you find a reconnection time, which is very significantly smaller than the one that would be given by pure resistive MHD, right? Still, at the end, you find that the reconnection time is still too large by a factor of 2 to 3. And there, the reason that at least two missing ingredients. One are all these FLR effects I was mentioning before, the final Landau radius effects, which are not all implemented in this simulation. And also another ingredient which is actually important, which is the skin depth effect, or the electron inertia, which was a dj over dt, which appeared in the generalized MHD equation, Ohm's law. So that's how it looks like. That's one example. There are several codes which are able to do that. M3D, Nimrod, I think. This is Xtor and others. So you see it started as it should with nested magnetic surfaces. And you see now a mode which appears here, which is an island, actually. It's going, expelling the hot core, which is here. And then you see suddenly the whole thing is becoming very messy. But then at the end, you are back to the initial situations. And you do that again and again. Now, what is very difficult, actually, in this problem is that you can quite easily find a crash, right? You initiate your code with a situation which is linearly unstable, is going to evolve violently, and will be a relaxation. What is very difficult is to find a cycle. That is a recovery, crash, right? That's very tricky. And that's actually an example of that, so where it gives actually you the pressure versus time normalized to the Alban time, and where you find several places the evolution of this of the pressure, and you find that of course this is a recovery phase, this is a crash. There is still some activity after the crash, then it's quiet, it starts again. Right? And in terms of magnetic topology, the reason for this is that for the speed up of the reconnection process is related to a strong change of topology. This is a Poincaré map. So what you're doing is that you're following field lines, and every time a field line is crossing a poloidal plane, you draw a point, right? So it's a Poincaré map. On the left, you have the case of single fluid MHD, and the case is two fluid MHD. So this is the hot core. This is the island that is replacing progressively the hot core. Right, and you see there is this line here. In fact, there are two so-called X points here, and a line here where this reconnection is taking place. Right, and this is actually predicted by theory, by the way. I mean, there are good predictions for that. And what is going on? That the whole thing is piling up here on this line, and that's why it's quite slow. Of course, you have to look in the details to be convinced of that. The big difference in two fluid MHD, and that's been found by many people, is that if you look at the topology, same thing, that's a Poincaré map, you find that there is now only one X point, essentially. It's very much deformed. That's because, essentially, the speed of your electrons in particular is this electron velocity, the flow plus electron magnetic velocity. It's deforming a lot, this thing here. So you see, it's like, you know, a droplet. And most of the reconnection now is taking place in one X point only, right? And if you look at the detail of what is going on in the inertial layer, right, and the reconnection layer, you find that indeed this is a situation where you expect a faster reconnection, right? So this is not too bad, except that in principle we should add a bit more physics. Now, I wanted to say that, I'm getting out for 2 slides of the internal kink mode, that the story of diamagnetic stabilization and cycles for oscillation, relaxation oscillations, is very generic, because if you look at the edge localized modes, which is another type of instability which takes place in the edge of tokamaks, it's kind of a similar process, although the modes, which is quite different. Well, part of it can be an external kink mode, so it's still driven by a current, but part of it is very often due to the pressure gradient. It's a ballooning mode, so that's different. Nevertheless, there are many common features. It's a fast relaxation it leads to fast relaxation of that pressure, same thing, 100 microseconds, and then a recovery phase, and so on and so on. And of course, it can be very detrimental to plasma-facing components, because every time there is a relaxation, some energy is arriving on a short time scale on the plasma-facing components. So this is an example giving you, actually I don't remember what exactly, but versus time, and you see this oscillation relaxation. And this one was actually modeled with another code whose name is Zorak, but same thing. You can put a B fluid or 2 fluid MHD or single fluid MHD. It's using reduced MHD. The other one is using full MHD. And you see it's very similar. I mean, if you move to single fluid MHD, you see one crash, and that's it. Game is over, right? No recovery phase. Right? Now, if you account for two fluid MHD, you are going to find something which is actually looking like relaxation oscillations, right? And of course, the physics is different, but probably it has to do with a nonlinear loss of diamagnetic stabilization in both cases. So see, it's very, very generic in the end. So I'm going to finish with the most difficult situation, which is the case where you include in the situation, or you account for fast particles, so typically alpha particles, which are the 3.5 MeV particles produced by fusion reactions, but it can be also particles produced by heating systems, so neutral beam injection or RF, radio frequency heating, particular ion cyclotron resonance heating. And in this case, you can see that you move to situations which are very different from the reconnection process I showed before. And the problem with these kind of modes, in that case are called fishbones, is that they can lead to a situation where you lose fast ions. And of course, this is not good at all, right? Because if you lose the alpha particles which are supposed to heat your plasma, right, then you're in bad shape. So that's why there is some concern about that. Anyway, so basically what is done usually in the literature is that you model thermal electron and ions with an MHD code, and you use a PIC code to model the fast ions, right? And one thing which is kind of a graal in that field is that very often experimentally you see a frequency chirping, that is a change of the frequency of the mode, which is attributed to very complex dynamics in the phase space of fast particles. And that's actually a very good test for testing the modes. So this is an example that was done by Fu with M3D. So in that case, so he's using MHD coupled to the so-called symplectic formulation of the gyrokinetic equation. That is gyrokinetic equation using E and B, right? And here you find actually again the mode structure in a poloidal plane. There is not much to say about that, but if you look at the mode frequency or the structure of the mode versus time, you see that versus time there are small wiggling here, which correspond in fact to this change of frequency I was talking about. Now the mode is driven essentially by a resonance between the mode itself, right, the kink mode, and the precession frequency of trapped particles, if you're dealing with ICRH at least, in your inside Q equals 1. And that's why it's difficult to capture. Now, to give you an idea of why it is difficult, or impossible, in fact, to simulate with fluid equations, if you look at the phase space, so this is another simulation by Vlad with another code. This is actually reduced MHD coupled to a PIC code. If you look at the phase space, so this is poloidal angle, and this is a kinetic momentum. Well, at the beginning, there is not much to say, but then with time, you see these very intricate structures, right? Which correspond actually to these clumps or holes that Jim mentioned briefly at some point. And of course, these structures here makes the distribution functions very far from a Maxwellian, right? And that's why, of course, you cannot model that with moment equations, right? And that's the reason that at least for this kind of instabilities, you have to use a hybrid code. Now, the problem of all this, well, there are several. One is this question of ordering, right, which is a bit of a mess. The other problem is that if you use conventional or two-fluid MHD equations for thermal ions, you're obviously missing this problem, or you're relying on this story of gyroviscous cancellations, and you're missing part of the physics for fine Lamb radius effects, right? So either you move to better descriptions like the one proposed by Ramos, but that's tricky, or you're daring and you move to 6-dimensional. That is, you get rid of the gyrokinetic approximation. Now, of course, you're not going to simulate the 10 to the 23 particles, as you mentioned, no way. So what you do is that you do a PIC, a six-dimensional equation, so you're dealing with microparticles. And you try to solve for it not only for fast ions, but also, if you can, for thermal ions. If you do that, of course, you solve this nasty story of gyroviscous cancellation, right? Because the gyroviscous tensor is going to be calculated exactly, well, up to the accuracy of your code, and that's not a detail. And you avoid also this question of consistency between, in terms of ordering between gyrokinetics and MHD. And also, of course, the equation of motion is very simple, right? It's just E plus V cross B in the Newton's equation. So you don't have to deal or to think about what you should average or not, and so on and so on. Now, of course, there are drawbacks you can imagine, because you need a large number of particles to simulate, especially if you want to include thermal ions, right? And the convergence is only 1 over square root of n, right, in the Monte Carlo code. So it's a long way. And of course, even if you do that only for ions, that means the time step has to be a fraction of the cyclotron time step, or cyclotron period, sorry. So that means your time step will have to be very small. But it turns out that our colleagues at the École Polytechnique decided to move in that way. And actually, the code is operational. And they started testing it. And this is actually a very recent, very fresh result, which actually shows you the growth rate of the internal kink mode. So I'm not talking about the Fishbone, but the internal kink mode, versus the fraction of hot particles. So this is the beta. Beta is the ratio of the pressure to the magnetic pressure, kinetic pressure to magnetic pressure. And actually, this is beta thermal here. It's a mistake. And that's the percentage of energy contained in the hot particles, so energetic particles compared to the thermal particles. And you see that when you increase this ratio, the growth rate decreases. And that corresponds actually to a very well-known prediction. Actually, it's a Krivka-Obermann 58, which is very well known. Plus, well, when for SOTIS, of course, it corresponds to the stabilization of the internal kink mode by the Hasty-Porcelli copy thing. So, at least some ingredients of what is known for fast and thermal ions, the effect of fast and thermal ions on the internal kink modes are recovered. So it sounds promising, but of course we'll see what it gives in more complex situations. Okay, so I'm arriving to the conclusions. Well, thing is that if you want to do MHD, as long as you are dealing with high frequencies and large scale, it's okay. You have to be careful. If you want to move to low frequency, which is the case of an internal kink mode, which is just a few kilohertz in practice, right? So much lower than the inverse of the Alventine. Then you have to put more ingredients, right? So the minimum you should put are 2 fluid effects, right? So that's what I showed, and it's now quite standard. If you want more, that is a kinetic effect like fast orbit wave, finite orbit wave, or let's say fine Lamont radius effect, and Landau damping, you can do that with closure schemes, but in practice it's not done much because it's very tricky. If you move to a situation where there is a resonance, that is, the particles have a resonance or driving resonantly the mode, then you have to move to a hybrid code where you couple a fluid code with a kinetic code. Actually, some also tried full kinetic, I think, in Japan, but that's difficult. So hybrid codes can be handled, except that there is this difficulty of writing correctly the equations, especially for the gyrokinetic part, but also the equation of ordering, which can be broken in some cases. So at this point, either you are very brave and you program the Ramos or equivalent as a set of equations to get something, or you move to 6-dimensional, and that seems to be the trend, at least here in France. That's what I wanted to say. Thank you very much.
Yes, thank you very much. Okay. Yes, so there are time for questions. So we are supposed to use that. Wait a minute.
I was wondering for the time scale. So typically MHD simulation, especially if you're going to several thousands of alpha times, you do implicit simulations, and for the kinetic, you use very small time steps. So what is the strategy? Are these hybrid codes always completely explicit as well for the MHD part as for the kinetic part, or is the...
Usually you have to do some substepping for the kinetic part, that's for sure. For the MHD part, you still use, of course, implicit, you have to, or semi-implicit, that's for sure. As far as I know, for the kinetic part, it's explicit, fully explicit. Then what is being done, if you think about an Alvan time, so it's 10 to the 6, second minus 1. Now, a cyclotron frequency is 100 megahertz, so that's 10 to minus 8, so that's 2 orders of magnitude in between. Then, of course, you have to choose a time step which is smaller than that. But in some of these schemes, in particular, they're using a Boris scheme. You just need apparently 8 or 16 time steps over one period, right? Cyclotron period. So it's something like 100 and 1,000 in between the Alvan time and the time step that is actually being used. Apparently, it's doable. Now, if you think about, incidentally, about gyrokinetic simulations like Gisela or so on, if you look at the time step, it's not that far from the cyclotron frequency. Of course, it's longer, but it's just 2 orders of magnitude or even less than that. So we are not that far from that, in fact.
Yes, okay.
Logic of development from MHD to kinetic development is similar to inertial fusion,
So,
but we also care with radiation effect. Certainly the charge is higher, but in your case you have a cyclotron emission, and certainly there is a reabsorption, but transport with radiation, does it important in the case?
No, radiative transport is not important. But radiation can be important, but then it appears essentially as sink terms in the pressure equations. So where you had either line radiation, Bremsstrahlung, and cyclotron emission. In present-day tokamaks, Bremsstrahlung and cyclotron emission are quite small, and it will be important in reactors, but not in present-day tokamaks. What can be very important are line radiation for heavy components. But then in practice, what is being done is, as I said, to add a sink term in the pressure equation, a cooling term in the pressure equation. But there is nothing like the equation that Laurent showed before, that is a radiative transfer equation. No.
My question is, how do you treat the non-linearities in your code, for example? Because you said you have an implicit code.
How do you treat the non-linearity associated to the, you mean the parallel pressure gradient in the Ohm's law or something like that?
Because if you have an implicit code, you make a large time step, you have to take properly into account the non-linearity, not to...
Of course, yeah.
But do you make some kind of iteration or...
Well, it's in the semi-implicit, of course, as you know, you have to invert matrix and so on to get your stuff. But the time step is, when I'm saying that you speed up the reconnection process, still the time scale is 100 microseconds, right? The Alvan time is 1 microsecond. So it's still much slower than the Alvan time. So the non-linearity is in those codes, in the MHD codes, are treated in a way such that you can treat even ideal MHD modes, right? Alvan time. So you can very easily handle, in principle, in terms of time step, something whose time scale is 100 microseconds, that is 100 Alvan time. So it's not a big deal, actually. It's more like just to finish that you do not describe very well in those code what is going on in the inertial layer, whose width is very small. So it's a question of spatial. It's more a question of grid. You know, it is very often in these simulations the grid is not fine enough to describe very well the nonlinear physics that is involved. So it's more in space than in time. I think the problem is hidden.
Okay, perhaps one more question.
So thank you, Xavier, for this nice talk. I just want to ask you questions that I have been very often asked recently. It's about gyrokinetic ordering. So what you show us, it was the problem of coupling of MHD fields with gyrokinetic equations. And you show us that the small parameter is E phi over T. It's always written down in early works like that, but since DMITS of 2005, I think, it was discussed how to couple flows, strong flows, with gyrokinetic equation. And I think that it comes back to the same issue as you. So now if you go back to the work of Brizard and Ham of 2007, what they propose from their conceptual point of view to say that the real gyrokinetic small parameter is K per row times E phi over T. Then in this case, you can always say that your gyrokinetic theory works for drift kinetic regime, because if E phi over T is order of 1, then you can still be working in drift kinetic regime. So if you have time, I just would like to have a discussion with you about
I would
that.
be pleased of that, because
Yeah.
I've seen some of these works, and you're right, it exists. I mean, there are several works addressing this question. The problem is, at the end, to deal with equations which are tractable, right? So you will show me what you have in hands, and we'll see
because
whether it
also
can be
saying that
programmed.
symplectic, there is equivalence between symplectic and Hamiltonian writing of a question. So I understand that probably it's more useful symplectic representation in this case, but I would like to discuss it with you. Yeah.
Good.
Thank you.
Thank you. Okay, so thank you everybody, and thank you again for the speaker.